So let's take a look at the chapter that deals with chemical bonding. And really, what happens a lot of times is this chapter is taught conventionally at the beginning of the school year rather than the end. And the reason I choose to do it at the end is because they refer to a lot of things like ionic radius and covalent radius and all these things that don't really mean much to students when they haven't even made compounds yet. So I choose to do this chapter quite a bit later so we can have a lot of chemistry under our belt, writing compounds and so on. And so this also allows students to already understand some of those bigger concepts, and so then they can look at it more in retrospect afterwards. This is a good chapter also to take a look at the applications. When you think about even, in the material world, when you're making paint, the question is, can you put this paint in an aerosol? Is it like a medical thing where a pharmacist can actually construct some compounds and make it so small that it can go through the skin and so on? Or do you have to have it in terms of an injection? So there's a lot of different things that you can do with this particular chapter and what it's good for. So taking a look at this chapter as we move forward, it's more, and just keep in mind that we already know a lot of chemistry. We already know how to write compounds. We've done all these things. And so we're just looking at some terminology that applies to things that we already know. So as we move forward with it, keep in mind where the periodic table and how the periodic table is set up. We're going to take a look at, for example, the atomic size or atomic radius of something. And so the question is, when we're talking about those, don't be thinking about the ions. Don't think about the plus ones and the plus twos. These are the stable element, and how big is that particular atom as they go in. So here's the trend. As you go across the period, it is actually the atomic size is going to decrease. As you go down the energy levels, then it's going to increase. Now, this is actually kind of a hidden one. This is a surprising one for people, that it actually decreases as you go over because, for example, we take a look at row 4, and we're starting with potassium here, element number 19. And as we add up, we go over to krypton, element number 36. Well, ironically, we wouldn't expect it to actually get smaller this way until you think about what's actually happening. See, those element numbers are actually made according to the number of protons within the nucleus. It's not anything to do with the electrons, because we already know electrons are gained or lost quite easily. Well, if you take a look at elements that are defined by the number of protons, think about where the protons are. They're in the center. They're in the nucleus. And so what ends up happening is, in essence, what's going to happen is those protons are going to bring the electrons in closer. So actually think about it like a magnet. The magnet gets bigger and stronger as you go across, so that pulls the electrons in closer. That makes the atomic size smaller as you go across. And that's how you want to think about that particular question. Now, as you go down this way, it does make sense to increase as you go down the energy levels, because we're adding even though we're adding bigger and bigger magnets in the core, we're also adding energy levels. So the number of shells that goes on and so on, that would cause it to go larger. There is a lab that deals with this, taking a look at some trends of the atomic size and the ionic size and so on. So we'll be taking a look at those. Now, in taking a look at the cartoon of this, it's a pretty lame one, but what it's talking about is thinking about atoms versus elements. Okay, atoms versus ions. And so the ion itself, this is something that's coming up a little bit later in this tutorial. When we think about lithium and we think about the lithium ion, and the question is, which one's going to be bigger? Well, you got to think about the particular charge on this. It's plus charge. That means that it lost an electron, so that means it got a little bit smaller. On the other side of the window, bringing those things in, being more attractive, is like for fluorine, for example. Well, fluorine as an ion, the fluoride ion, that's going to gain an electron, which means it's actually going to become a little bit bigger. And so that's the only point behind that particular cartoon. Now, here's a new term for us called first ionization energy. Okay, again, we have the periodic table down below. And so the definition of this, first ionization energy, is the amount of energy required to remove an electron. So let's think about those particular ions as we went through. That's going to help us really reason through this a little bit. As we move over to the right, what we're finding is these guys are positive, 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 and then all of a sudden we flip the switch right here and it becomes negative ions. So let's go back to our definition. The amount of energy required to remove an electron. Well, wait a minute. On this side, they want to gain electrons. On this side, they want to lose. So how much energy does it take? How much convincing does it take to talk lithium into giving up an electron? Well, not much energy, okay? If we take a look at fluorine, for example, that one wants to take in electrons. So how much convincing would it take to remove electrons when it really wants to take them in? Well, that would be a lot of energy. So you see that the first ionization energy increases as you go toward the right, because those are going to be negatively charged ions. It's going to take a lot of convincing. Now, as we go down, we'll find that that actually doesn't take much convincing at all. Think about it like this. If you're on a field trip, and you're on a field trip with only 9 students on the bus, okay? It's going to be pretty noticeable if you lose one of the students on the bus if you have only 9. But if you have 117 students, it's going to be really easy to lose those electrons or those students in this example. So the amount of energy required to remove an electron, when you got more kids out there partying around, it's going to be really easy to get rid of those. And that's how I think about first ionization energy and so on with that type of example. The more electrons, it's pretty easy to lose those. When we only have a couple in the first place, then it takes a lot. So that's why it explains that decreasing as you go down the periodic table. Now, how about bond formations? Okay, bond formations is a function of this transfer of electricity of electrons. Okay, so electronegativity, otherwise known as, and there's synonyms to one another as electron affinity. Electronegativity is actually a number value, and then electron affinity is just its overall characteristic, how much it wants to take in or not. So, or if it wants to take in. So there is a difference between the two. One is a number value, and one is just a general statement. So the question when we're talking about those two is a little bit different than when we're talking about first ionization. First ionization was saying, how much energy does it take to give up electrons? When we take a look at electronegativity or affinity, how much do these things want to take in electrons? That's the question. Well, remember, lithium wants to give up electrons. Okay, so it doesn't have much of that electronegativity at all. Fluorine is the one that wants to bring in those. So that's where it would make sense as you go down. And for also with that is the same concept. As you add in a ton of electrons, it really doesn't want to take in more. Think about the really, really large families. Having another kid, really, that amount is not very, you don't want to add to that. But if you have only a couple kids in there in the family, then yeah, its tendency to bring in more, have more is pretty high. So it decreases as you go down the energy levels. And so as we take a look at the most active metals, they're the ones with the lowest electronegativity values. Remember, our active metals are going to be over here. And so as you go across the period, it increases. That's low on this side. And as you decrease going down, so here's our more active metals as we go. Now, here, like I said, electronegativity is a number value. So this is the electronegativity values that we would see. And you see that, in fact, exactly what I just said. As you go over and as you go down, we're going to see those trends, okay? Now, these numbers are things that you're going to be going back to do something else. And that deals with the type of bond that's going to be in there. Okay, so the strength of a bond is something that we've already looked at. If we take a look at the energy in like a stoichiometry problem, we said how much energy was in there. Well, the question is, how do we know that? How much energy is available in a particular bond is a function of its electronegativity values. The stronger the difference, not the negativities themselves, the stronger the difference is the stronger the bond strength. So if we see the electronegativity difference is a value of 1.90, this is how much energy is available. Now, this is kilojoules per mole. Think about it in the United States term, it'd be like calories per mole. So we can actually figure and calculate out how much energy is in there available in a particular bond. Now, if it has a really low difference, there's not as much energy available to it. Okay, so that's how we know those things. These aren't values that you need to know off the top of your head, but it's just showing you how we would know if something is there. So the question is, what do we do with this? All right. We use those values to actually figure out what are those traits? What are those characters of the different types of bonds? Okay. Kind of a joke with the James Bond type movies. But when you think about it, those bonds we always describe in kind of humanistic features anyway. So we take a look at bond characters in chemistry. If there is a high difference of those electronegativities, What that means is that electrons are actually being transferred, going from one to another completely. That was what we would define as an ionic bond. But if there's a very low difference between those, it means that those electrons are being shared freely back and forth. And that sharing of electrons refers to a covalent bond. Okay, so we can actually go through and tell if something is ionic or covalent based on electronegativity values. Okay, from there, what we know, and we've actually seen this before, we know that things are going to be ionic. If we know they are ionic or covalent, then we can predict things. Okay, ionic, a really good example would be like sodium chloride, very hard to melt salt, very soluble to dissolve salt. It forms crystals and it's very conductive. If it's a covalent bond, it has very low melting points. I think of water as a really good example. I can melt water just in my hand. Okay, it's not as soluble with things. It's brittle when it is a solid, and it's not conductive. Okay, so pure water versus water that has contaminants in it, but pure water doesn't actually conduct electricity at all. Okay, so that's one thing that's in there that tells us the traits of those particular bonds. So that begs the question, what is a high value and what is low? Because I just showed you some examples of numbers. So the question is, what's a high value and low value? Here's a magic number. That's the dividing line. That number, the difference between electronegativities, that magic number is 1.67. If you find the difference is less than 1.67, it tends to be a covalent bond. If it's more than 1.67, it tends to be an ionic bond. So here's what we see as we take a look. If I give you any old example, so we'd say we'll take this element and we'll mix it with this element, and I want to figure out if that's going to be ionic or covalent, or I want to know if it's going to be conductive or not. I simply refer to this and I see 0.9 and I subtract it from 2.6. So it's going to be a difference of 1.5, or sorry, 1.7. Well, that's just slightly more than that 1.67 value. So I would say that it's going to be slightly ionic. Okay, you just find the difference in electronegativities. So here's an example of how we would do that. We've in the past said, and I kind of cheated at the beginning because I said, well, let's just look and see if it has a metal in it. Metals tend to form ionic bonds. So here I have an example of magnesium and oxygen. Well, those values of 3.44 minus 1.31, those are the values of electronegativities for those two elements. That difference is 2.13. Based on this number, now I can say, yes, it's ionic. If I were to take a look at boron versus phosphorus, now in the past, and this has always worked for us, they're nonmetals stuck together. So we would say it's covalent, but now let's prove it. Okay, so the electronegativity values from that chart was 2.19 minus 2.04, a difference of 1.15, so then it would be covalent. So that's what I want you to do, is prove if it's ionic or covalent. Don't just say it, because we could probably eyeball it and say, oh, there's a metal, that's going to be ionic. There's a metal, that's going to be ionic. It's true most of the time, but we do want to prove it with the math, the differences there. Now, taking a look at other types of things about bonds, we see that our bond angles and everything else we learned in Vesper. Okay, in this last chapter we just did, we saw that they were shared and they would be unshared, and we saw angles and all those other things. But now we can also say the size of this compound. Okay, again, this goes into some other practical applications with paints, with adhesives, with medicine that we want to try to get transdermal to go through your skin. All of those things we could do. So we want to see how big this distance is to figure out how big this overall molecule or compound is. Well, all I'd have to do is find its internuclear distance, the distance from one nucleus to another. Okay, there's a couple things you want to take a look at when we're looking at this bond length, this length of this chemical bond here, if it's shared or if it's going to be an ionic compound where it's going to be donated. Okay, so here's what happens if we're dealing with an ionic compound. When we take a look at just an atom here, we have to look at what the atom is. If this is a cation, we know that's going to lose some electrons. As it loses electrons, its ionic radius is going to get a little shorter. If this is going to be my anion, what he would do is, compared to the stable atom, if it's going to be an anion, he's going to gain electrons. So he's going to actually get a little bit bigger. So the ionic radius, we have to stop and ask, what is the actual type of ion there? Is it going to be a cation or is it going to be an anion? And we can go from there. Now, if we're looking at a bond length, it doesn't matter, because whatever, say, for example, this guy is going to lose 2 electrons. Well, where are they going to go? They're going to go here. So if he loses 2, this guy would gain 2. So it ends up being about the same. The bond length is usually just the sum of the individual radii, maybe a little bit less because they are going to stick together and kind of squish together a little bit different. And so that kind of brings up to this back side. The non-bonded side is what we refer to as the van der Waals radius. Okay, van der Waals radius says this: when we're putting these elements together and they're forming a bond, doesn't matter if it's covalent or ionic, what's going to happen is these sides are going to be pulled in closer to one another, kind of squished together, if you will. And the effect of that, because there's electrons that are flying around the whole thing, the effect of this side, the bonded side being squished in, the back side is going to be bulged out a little bit. So that's why I say the radius of the van der Waals is going to be greater than the radius of the ionic or covalent radii. Doesn't matter which one. It's just going to be, just one of those things to be aware of. The back side, the non-bonded sides, are going to be just a little bit bigger than the sides that are bonded. Okay, so keep in mind these terms when we're referring to things. We're talking about just the axis, the line joining the two nuclei together. We can from there figure out the angle, and that's what we did with Vesper theory. Okay, the angle between the two bond axes. Remember, we had a 120, 1 a 9.5, and all that fun stuff. So we can figure out what the angle is with that. And we can also now figure out the distance, okay, that entire bond length, the distance between the nuclei. And that's going to be a little bit different, everyone's. We're going to talk in general terms. That distance is going to be a little bit different, kind of a ballpark, because those molecules are constantly moving. They'll be bending, they'll be rotating, they'll be stretching symmetrically. So if you have three elements, they're going to be both going the same direction, or maybe they're going to go asymmetrical. And so there's going to be some vibrations and so on going along there. So these are just things to be aware of. Again, when we're taking a look at bond lengths, all we're doing is we're just adding up the different radii to find the total bond length, okay, how big that molecule is. And by the way, you saw a PM on there, and you'll see it again. That PM stands for picometers, so we actually have a distance here. Now, I want to remind you again, one more thing. When we're talking about atomic size here, we're not considering the ions. So as we go across, we need to realize and just keep in mind that the atoms actually get smaller as you go across, but they do get bigger as you go down because of the added energy levels in shells, okay? So we know that the sizes of things are going to vary based off of those. And there's just values that you look up on the back of your periodic tables or other values that are supplied, okay? That's what we want to take a look at with atomic size and radius. You don't consider the ions in there because when we have ionic size and everything else, when one gives up 3 electrons, the other one must take them in. So it's a little bit different that way. Okay. Now, ionic radii, and here's where your question comes in, kind of a review one. This should make sense by now. If we consider the stable atom and we want to look at something that's going to give up electrons, they're going to or in this case, we've got the anions. So I've got anions listed first. It's going to be your negative ion. Well, that's going to be taking in electrons, so it's going to get a little bit bigger when compared to the stable atom. When we have a cation, the thing that's going to give up electrons, that's our positive ions. Well, giving up electrons means that it's going to become a little bit smaller when compared to the stable atom. Okay, so you just add up the two to get the internuclear distance. That's how you do that one. Now, when we have a covalent radii, remember that those electrons are bouncing back and forth. So you don't take a look at, just add the internuclear distance. Usually what you do is you take a look at what the distance of just one of those atoms are. So take a look at this example. We have chlorine gas, we have iodine gas, and I want to know how big is iodine chloride. Okay, it's kind of a weird combination there to have those two together, but it is one of those things that electrons are shared back and forth. Well, here's how we figure those things out if they're diatomics. For example, we have chlorine gas. We know that distance with those two chlorines there. I don't know what the distance of just chlorine itself is. I know the ion when it's ionic, but when it's covalent, we have to do something different. So we see that chlorine gas has an internuclear distance of 199 picometers. Well, that means that if the electrons are just bouncing back and forth, it means that one of these chlorines is going to have just a 99.5 picometer size. The iodine would be 266, that's just referenced, two iodines sharing back and forth, that means that one distance of just that one element of one iodine is going to be 133. So I can use this information, knowing these two, I can use it to figure, okay, what is just one of them? And then I simply add them up. And so that I would know that my iodine chloride would, based on this information, have an internuclear distance of 233. Okay, so I noticed that I just rounded with those things. I rounded according to significant figures. We go to the ones place in this one because this is the tenths place. So that's where I got the 233 from. It's not that big a deal. Now, remember the van der Waals. That's the back side, the non-bonded side. Just keep in mind that those are going to be slightly greater than the shared side, okay? So it's going to be, because electrons are going to be repelling one another, they're going to be forced closer together on the bonded side. That makes sense. So the back side is going to bulge out. So just think about taking a balloon and squishing it up against another balloon. It'll get flat on the side that they're squished against. The back side will bulge out. That's all you need to know. The squishing of the electron cloud on the backside forces it out there. Okay, so now take a look at the different types of radii, because this last piece was all about just dealing with sizes and distances and so on. The atomic radius is going to be just something that you measure, and remember that it increases as you go down, but it decreases as you go to the right. Ionic radii, well, we've got to slow down. It will be different. Sometimes it gets bigger than the atom. Sometimes it gets smaller based on if it gains or loses the electrons. So slow down and think about that question first before you write down which one's going to be bigger. When we have a covalent radius, remember it is going to slightly get smaller than the atomic radii due to the sharing of electrons. So typically you're going to see how big one compound that's diatomic and go from there. But it's going to be just slightly less than the atomic radii based off of that. Okay, it can be a little bit greater when we see multiple atoms all in there because they're pulling in different directions, but usually we find it a little bit less. And then van der Waals radius is going to be the one that is almost always just a little bit bigger than the atomic radii because it's going to be bulge. It should be around the same. If you're going to find the bonded side is going to be a little bit smaller. The van der Waals is going to be a little bit bigger. It should be around the same, but technically it's going to be just a little bit bigger than what we'd find in atomic. Now, the question you guys might have is, what am I supposed to do with all that, right? Well, you're going to get some scenarios where it's like, which one would you consider to be bigger? The atomic radii of this, when given in examples like salt, would you expect the atomic radius to be greater than, less than, or equal to, and when you compare these different things? So that's what's coming with this. Take a look at sodium itself. Take a look at the sodium ion. Okay, which one's going to be bigger? What if it's going to be shared with like water? What's going to be bigger, the oxygen atom or the covalent bond when it's bonded to the hydrogen and so on? So that's the type of question that's going to be asked with this. And again, don't overthink these. You want to approach it the right way. Know your definitions, but just think about the different scenarios with it, and you should be able to comment on it because you've done a lot of chemistry. All these terms make sense now. I still struggle with people that teach us that maybe a little bit too early. They teach these types of trends before kids have even made ions yet. Before they've even made some compounds, they don't even know what that's all about and what's really going on there. So this is why I save these types of trends, these periodic trends and these other things about the size and everything else. I wait until much later because we've known a lot of chemistry and see how that can work. Okay, good luck. You're going to be seeing a lot of the practice questions with that. And this is just a quick tutorial. You're going to need to slow down and go back and see some of those and put them into practice.